Today we will discuss on a very interesting topic, that is MEMS for space applications. Already we discussed on the accelerometer as well as gyro chip, which are also used in spacecraft technology, but topic which I will discuss today is only meant for satellites. Positioning a satellite in a particular orbit is an important issue. So, how the MEMS devices is playing an important role for satellite positioning, that is the topic of discussion in today's lecture. You know, whatever the either aeroplane or satellite or the missile, whatever you are going to send in space, one of the major concern is the weight. So, miniaturization is one of the important issue. Miniaturization of the devices and different components is one of the major issue when you are going to integrate them either in a spacecraft or aeroplane or missile, wherever it is. So, the weight and small weight, miniature size is the issue, and you know MEMS will give you a process or a technology where you can miniaturize the devices as much as possible with lot of micromechanical action also. So, today we will discuss on micro thrusters, which are basically used for picosatellite program. Microsatellite and picosatellite is a topic of research today in many of the advanced level institutions around the globe. So, Indian Space Research Organization ISRO is also thinking in near future for microsatellite or picosatellite program. So, they have initiated an R&D effort to miniaturize different components and to get highly reliable, space qualified, small mass and small size devices, which may be helpful for reducing the weight of the space vehicle. So, one interesting area in space market today is to reduce cost and increase reliability. So, micro propulsion is one example of the application of the MEMS to the space environment. So, my focus on discussion of today's lecture is micro propulsion system. The main application of the micro thruster is the micro propulsion for microsatellite, means whose weight is within 20 to 100 kilo, and nanosatellites whose complete weight is less than 20 kg. So, that is for those satellites, how those satellites will be positioned accurately in a particular orbital system by using a small sized micro thruster that we will see today in today's lecture. Now, what is the propulsion? In a broad sense, propulsion is the act of changing the motion of the body. So, when you are sending a spacecraft in space, so you have to many times you have to change the motion of the spacecraft, so that you can accurately position the space vehicle in a particular orbital location. So, to changing its motion, that is done remotely, okay, and by using certain devices which is known as the thruster. You have to put some pressure, so that the whole satellite could be changed from one location to another location. So, propulsion mechanism provides a force that moves bodies that are initially at rest, then change of velocity will take place, that is the propulsion. So, basically propulsion means it has to change its velocity or motion from rest, so that the bodies will move which were initially at rest. Rocket propulsion provides thrust by ejecting stored matter called propellant. So, that is the material which is known as propellant. There are various kinds of propellant. Lot of research is going on in the propellant, high efficiency propellant. Some of the propellant examples I will cite also today. So, that is the one major materials research in propellant side. Using propellant, how rocket propulsion can take place by using micro thruster, that we will see today. Now, what are the issues? What are the different classification of the propulsion system? They can be classified according to different categories. One is type of energy source, that whether the energy source is chemical, nuclear or solar. Depending on the type, different class of propulsion systems are there. Second category is a basic function, whether function of the propulsion is attitude control or orbit station keeping, east-west orbit station keeping or north-south orbit station keeping. That is one of the function of the microthrusters which use certain propellants. Attitude control, attitude of the space satellite, that you can control. Third one is type of vehicle, which kind of vehicle you are using. It may be aircraft, it may be missile. Its size, type of propellant, type of construction and method of producing thrust. These are various broad classifications based on which we can categorize a particular propulsion system. Now, what is thrust and impulse? There are certain parameters based on which the propulsion system is identified or is categorized. That is, one is thrust, that is the force produced by rocket propulsion systems acting upon a vehicle or reaction experienced by its structure due to the ejection of matter at high velocity. So, you see, basically the main principle behind is Newton's third law. So, that is, you are ejecting some of the fluids, and because of that in opposite direction you will getting certain thrust. Okay. That is the basic mechanism. Total impulse, which is known as IT. For constant thrust, the IT is given by F into T, where F is the thrust force and T is the burning time. That is known as the total impulse. Time multiplied by thrust force is called impulse. It is the total energy released by the propellant in a propulsion system, that is known as impulse, which is designated as IT. Other parameter is specific impulse, IS. One is total impulse, other is specific impulse. IS is defined as total impulse per unit weight of propellant. That means impulse per unit weight is known as specific impulse, which is known as IS. IS is the figure of merit of the performance of a rocket propulsion system, and impulse I basically F into dt, which is force is m star into V2 dot dt. So, that is written here, where F is m star V2, then IS is F dot dt divided by the m star g naught and dt, where g naught is the acceleration due to gravity, m star is the mass flow, okay, mass flow, this is acceleration, and dt is the time, and F is a thrust. So now if you simplify it, then F dot dt is given by m star v2 dt, then it comes to v2 by g naught. So that is the specific impulse is coming v2 by g naught, where g naught is acceleration due to gravity and v2 is the velocity in that direction. So another parameters are mass ratio, impulse to weight ratio, and thrust to weight ratio. Mass ratio is defined as ratio of mass, final mass mf and m naught, that is mf is final mass, m naught is before rocket operation. Okay? And parameter for analyzing flight information, that m mass ratio is one of the job is for to analyze flight performance. Impulse to weight ratio, that is total impulse IT divided by propellant loaded vehicle weight W naught. IT by W naught is the impulse to weight ratio. Its high value means efficient design. Impulse to weight ratio should be very high for a efficient propellant system. Another parameter is thrust to weight ratio. What is that? It expresses the acceleration F that the engine is capable of giving to its own loaded propulsion system mass. Thrust to weight ratio. Okay? So these are few parameters. Effective exhaust velocity, this is another parameter defined as average equivalent velocity at which propellant is ejected from the vehicle and is denoted by is dot g naught, which is nothing but F by m star. The thrust due to momentum change is given by F equal to dm dt into Vt, V2 is equal to m star dot V2, where V2 is the exhaust velocity. The pressure of the surrounding fluid also affects thrust. Because of change in ambient pressure due to variation in altitude. You see, with altitude the ambient pressure is going to change, and because of the change in ambient pressure, the total value of the thrust will be changed, because the exhaust velocity with altitude is going to change. Okay, because ambient pressure is different with altitude. So the F is given by m star V2 plus P2 minus P3 dot A2, where P2 is the nozzle exit pressure, P3 is external or atmospheric pressure, and A2 is a cross sectional area at nozzle exit. So P2 and P3 is the difference of pressure between the nozzle exit and the atmospheric pressure. So that parameter is going to change with altitude, and because of that total thrust F is going to change. To make P2 greater than P3, nozzle design is very important, because here P2 minus P3 one relates to directly relates to nozzle exit pressure, and the nozzle exit pressure depends on the design of the nozzle. When P2 equal to P3, then F is equal to m star dot V2 and is referred as the nozzle with optimum expansion ratio. When P2 equal to P3, at that particular moment the F equal to m star dot V2. Now thrust of propulsion system. There are certain issues which are mentioned here relating to thrust in a propulsion system. Thrust of a rocket unit is independent of the flight velocity. Change in ambient pressure affect the pressure thrust, that is, there is variation of the rocket thrust with altitude, that I mentioned. atmospheric pressure decreases with increase of altitude. So, the thrust and specific impulse will increase as the vehicle is propelled to higher altitudes. From that relation, it is coming directly. This change in pressure thrust due to altitude change can be 10 to 30% of the overall thrust. Variation may be 10 to 30% of the overall thrust. High specific impulse or high performance, this means high gas temperature and or low molecular mass. What is the gas temperature? That is which is ejecting from your the propulsion system, and low molecular mass. Next is the low absorption of moisture, which often causes chemical deterioration. Which chemical deterioration? Means the propellant is a chemical. If it absorbs moisture, then it cause some chemical deterioration, composition may change, and the efficiency of the propellant will also affect. Another issues of the propellant characteristics is that it should be safe, because the propellant which you are going to use, it should be safe, means safe in different aspects, safe from human hazard point of view and safe from environment pollution point of view, because when you are launching a satellite, the propellant is ejecting, and this should not create nuisance to the atmosphere which may deteriorate the environment for living beings. Okay. Low cost is another issue. It should be very simple and reproducible. These are some of the characteristics. Low technical risk, such as favorable history of prior applications. These are the technical risk. That means you know anything you are going to adopt in space, you have to know certain history, because any technical failure will lead to loss of enormous amount of not only effort but also money, because a particular program, satellite launching program, involves few hundred crores rather of money, rupees money. So you have to be properly ensured from the history of that total method. That means before sending anything to the space, you have to have in similar atmosphere lot of testing without taking any risk. So that testing is not space qualification. When everything is qualified in that environment, an artificial space environment is created in that particular lab, specially designed lab, including pressure. So there all the components or electronic functions are tested and satisfied over the period of time, then only it is used in any of the space vehicle for launching or any other function. Non-toxic exhaust gases, that already I told you, it should not create pollution or it should not disturb the environment or atmosphere. So what is the exhaust gases coming out of the propellant after burning? So it should not produce any non-toxic gases. So these are some of the characteristics. Some of the examples of the propellant is shown here. One is double base. Mixture of some compounds are sometimes used, sometimes simple some chemicals are also used. DBAPAL, Al is basically aluminium, AP is ammonium perchlorate. Sometimes a mixture of aluminium and HMX, which is cyclotetramethylene tetranitramine. So these are the few chemicals, and apart from those, for preliminary testing you can use simple water also as a propellant. For testing purpose you can use water also without going to that the chemicals which may be highly expensive or which may in some cases is not much user friendly. The advantages, these are solid propellants, because water is a liquid propellant, and this what I mentioned here, these are solid propellant. There are two kinds of propellant used, one is solid propellant, another is liquid propellant. Basically it has to burn and it has to produce some gases which will eject to the nozzle, as a result of which your device will push forward. A thrust is applied to the spacecraft or satellite, whatever it is. That is the basic objective. So the advantage of solid propellant are, it is a simple design, few or no moving part, will not leak or spill. If it is a liquid, there is a chances of leaking or spilling over, can be stopped and restored few times if programmed, can be stored for 5 to 25 years without any deterioration of the material. So this is the advantage. On the other hand, the disadvantage of solid propellant are also there. What are those? Explosion and fire potential is larger compared to liquid propellant. This is an explosive material most of the cases, and is a very prone to fire potential. Require an ignition system, because since it is a explosion, it has to be fired, you need an ignition system. Each restart require a separate ignition system. Once you start it, then the second chamber you have to stop, then again if you have to fire the second chamber, you have to again put an ignition system. So each time if you want to fire it, so you need an ignition system. Exhaust gases are usually toxic in case of the solid propellant. Some propellant can deteriorate in storage, which is known as self-decompose. Cannot be tested prior to use, because testing is highly risky, although sometimes it has to be done before actually implementation, but it is highly risky. Need very much safety precautions, because the total system is an explosive system and it involves lot of fire hazards. Now this liquid propellant. Liquid propellant are water, just I name it, water, ammonia and hydrogen. These are the three liquid propellants which are commonly used. Liquid propellant embraces all the various liquids used, and maybe one of the following. It may be oxidizer, that is liquid oxygen, nitric acid, etc., fuel, that is alcohol, liquid hydrogen, gasoline, etc., chemical compound or mixture of oxidizer and fuel ingredients capable of self decomposition. Any of the above, but with gelling agent, behaves as thick paint. If you put some gel with that, it will not spill but can flow under pressure. So one of the advantage in case of the solid propellant, we told that since it is solid, the spilling over problem will not be there, but in case of liquid with very low density, there is a leakage kind of thing and some spillover kind of things, always that problem is there. So people try to mix some gelling agent so that its density will be higher and problem of spilling over will be reduced. So these are the liquid propellant. Now advantages of liquid, this sorry, the heading is a solid, it should be liquid. Advantages of liquid propellant, it should be. It usually highest specific impulse, can be randomly stopped and restarted, which cannot be done in case of solid, can be largely checked out just prior to operation, can be tested at ground or launch pad prior to flight. Most propellant have non-toxic exhaust, which is environmentally acceptable. These are the plus point in case of liquid propellant. Now disadvantage of liquid propellants are this: a relatively complex design, more parts or component leads to more things to go wrong. Since it is a complex, lot of parts will be assembled and any of the small parts may go wrong, which will compel us to leave the complete module. Okay. Cryogenic propellant cannot be stored for long period except when tanks are well insulated. Now this cryogenic propellant people are thinking of. So in that case you have to have the tanks which is well insulated. This liquid oxygen or liquid nitrogen, liquid gases basically, these are the cryogenic propellant. Leaks or spills of several propellants can be hazardous, toxic, but this can be minimized with gelled propellants, which was mentioned in earlier slide also. Tanks need to be pressurized by separate pressurization system if want to eject the propellant efficiently. Few propellant gives toxic vapors, red fuming nitric acid in some of the propellant like hydrogen, that is not user friendly at all. Now if you compare the liquid versus solid propellant, then you can summarize like this. Liquid propellant engines seem to be preferred for space launched main propulsion units and upper stages because of their higher specific impulse, a relatively clean exhaust gases, etc. Favored for post boost control systems and altitude control system, that is the plus points of liquid propellants. On the other hand, solid propellant motors are preferred for missiles, air to air, air to surface, surface to air, short range surface to surface. For this kind of missiles, solid propellants are sometimes favored. It is also favored or preferred for ballistic missiles, long and short range surface to surface, because instant readiness, compactness and their lack of leaks of hazardous liquids are important criteria for this application. Okay. So these are the main features of liquid and solid, where to use liquid and where to use solid. This is the it depends on the choice of the applications. One is a space satellite, their preferred is liquid, and in case of missile program preferred is solid propellant. Now micropropulsion developments day by day, it proceed like that. Initially it is cold gas system, then switched over to bipropellant thruster, that means not a single material, it is a mixture of material either solid or liquid, then monopropellant thrusters, then colloid thrusters. Another kind of propulsion is a field emission electric, because no liquid or solid propulsion systems are used, is a field emission electric propellants sometimes used long time back. Plasma pulse thrusters PPT, micro ion thruster MU-IT, Hall effect thrusters, laser plasma thrusters, micro solid propellant thrusters, and lastly vaporizing liquid thruster VLT. So in case of the micro or pico satellite program, the VLT, vaporizing liquid thruster, is drawing lot of attention. Now we will just concentrate on the vaporizing liquid thruster, which is very promising and lot of research is going on in that direction. So vaporizing liquid microthruster VLT is a typical example of MEMS based micropropulsion device. It can be easily fabricated using MEMS technology, micromachining technology. The change of phase, what phase? Liquid to gas, is exploited to produce a thrust. Liquid we will use initially in the chamber, propulsion chamber, then we convert into gas and we will force the gas to eject from narrow nozzles, which will produce thrust. That is the basic principle. It requires a heating resistor, a vaporizing chamber, a nozzle, a propellant inlet and a micro channel. So these are the components of the microthruster. You have to have heating element, resistor. It may be embedded or it may be surface thin film resistance, which can be powered to heat any propellant. You have to have vaporizing chamber. For ejection of the propellant in gaseous form, you need a micro nozzle, and inlet and outlet of the propellants as well as the micro channel through which your liquid propellant will enter and gas will eject. So, micro channel has to be formed. All those things can be integrated together to have the micro thruster. If you have the technology for making micro nozzles, if you have the technology for making the that small channels which is called micro channels, and if you can etch the chamber or cavity in silicon which may act as a vaporizing chamber. Propellant can be fed into the thruster from a propellant tank by capillary force or pressure. For pushing the propellant into the cavity, if you have to use a pump, then again another addition of components is there, and which will increase the total weight of the microthruster as well as the cost also will increase. That is why in case of micro or pico program, so ordinary the capillary force or pressure inside the capillary is used to flow the propellant from the tank to the small capillaries inside the device through the micro channels basically. Now, here is a schematic diagram. Vaporizing liquid microthruster VLT. Different structure of VLT is proposed. Here one structure which is being used by researchers of University of California is shown here in the figure. You can see here the fluid input is here through the nozzle, and it is completely made of silicon, and here bottom piece is silicon and top piece is the glass, and you can see here is a vaporizing micro chamber which has been formed by micro machining silicon, and then here one small channel, and at the end there is a exit nozzle. So, now heater is used here, embedded heater into the silicon. Now, if you heat the silicon through that heater, then in the vaporization chamber the propellant phase will change from liquid to gases, and they will exit through the nozzle, as a result to which thrust will be created in opposite direction. If the gas propellant moves in this direction, and thrust will be there in opposite direction. So, that is the basic diagram of the edge nozzle microthruster. There is another category of microthruster which is this design is asymmetric, and here instead of bottom the heater was placed on the surface of the thruster. Since silicon is an excellent thermal conductor, just they heat, they are not directly heating the propellant at the surface of the silicon, but they are heating the complete silicon material. Some contacts are made here, then is a silicon is a good thermal conductor. So, here the propellants are injected in one hole, and now it is ejected. All the design are very crucial to get greater efficiency, and bottom plate is complete a Pyrex glass, and if this is the width, so here the height of the chamber is a half of that complete width of the silicon device. This is the nozzle, and here is the chamber, and here is another nozzle which may be the input and other is the output nozzle. Glass used to seal micro chambers, so called asymmetric design. Glass was used only to provide a window for visual observation of fluid flow. Since bottom piece is glass, you can easily see how the fluid are flowing through the chamber. Asymmetric means here the whole material is not made of same, whole structure is not made of same material, means bottom is glass and other is silicon. There are certain microsystems where both the pieces are silicon, it is a symmetrical structure, you can get it. So, this is some form of other form of the microsystem. Now, here in both the cases the basic principle is like this: vaporization of the fuel in the microchamber has a longer pre-vaporizing warm up time because heat is being delivered only to one side. Why one side? Because the heater you have put in one side only, in the silicon here, not in the bottom side. Bottom side is only glass. So, that side you have to give some warm up time, so that the complete thing heat will enough to change the phase from liquid to gases of the propellant. So, now even with the glass cover, the silicon containing diffused heaters provided sufficient thermal contact and conductivity to effectively heat the microchamber. This design is more power efficient and allows thermal input from heaters on both sides of the microchamber and utilizes the high thermal conductivity of silicon. Because you are fitting, if you want resistor in one side asymmetric, so your power requirement is less, but if you allow certain time, so obviously that is why they call it a sufficient thermal contact, you will get it, and is power efficient. Okay. Now, what is the fabrication procedure? Bottom was the glass and top was the silicon on which you are making nozzles, chambers, etc. So, they started with p-type silicon 100 and the oxidized thermal oxidation, which is 0.8 micron, photolithography for heater pattern. First you have to go for the designing or fabrication of the heater, which is embedded heater. The heater can be made using diffused resistance through silicon, and you can have this structure like meander line. So, just like coil, here instead of coil you are using some resistance which is a diffuse resistance into the silicon. Or if you put power, apply power to that, the embedded the coil embedded resistance into the silicon. So, it will be heated, and the heat, since silicon is a conducting metal, it will be transmitted into the propellant. So, phosphorus diffusion is made 10 to 11 ohm per square. Striped drive-in oxide, grow 500 angstrom thin stress relieving oxide DTO. That is the process which they followed. They means from where it has been is reported. They after that they grow 1500 angstrom LPCVD silicon nitride for insulation, double side alignment of for heaters, silicon etching to create microchamber nozzles and inlet holes. These are the three microstructures. One is the microchamber, another is the nozzle, and third is the inlet holes. Then bonding. Bonding is substrate to glass bonding. Shadow masking to pattern aluminum for electrical connection for diffuse heaters. Because at the end, if you make electrical connection, the complete structure is not exactly planar. So, you cannot go for the lithography, regular lithography. So, you have to go for shadow masking technique, which I mentioned in earlier classes also. By inside the vacuum chamber through some stencil, you can just make the pattern of metals for making contact. Now, this is another alternate microstructure structure which has been proposed in some literature. What they are doing, they are not using embedded heaters. Rather, instead of embedded heaters, they used here the thin film heaters. So, titanium material they have used for making heaters. You can see here is also there are two structure, one is the top, another is the bottom. What they do here is the inlet channel, because bottom wafer is the inlet channel. In earlier case you see this is a homogeneous structure, earlier is one glass and other is silicon, and both inlet and outlet are made in silicon, but here both are silicon piece, one inlet in the bottom piece and outlet in the top piece. So now in the bottom piece, other than this inlet, they are forming the heater, that is basically the titanium is patterned on the surface of the silicon, and then there is a cross sectional view. Obviously you cannot see the total meander line, you cannot see, only some patch, black patch you can see, and they have some leads, two leads, and in the top wafer, other than the nozzle, they have etched another hole, and through that hole they made the wire bonding. And after making the wire bonding, taking wires outside from the titanium heater, they fill at the end the hole using some glue, so that this is completely covered. So in that case, just directly you can heat the element. One advantage here compared to other is there, with minimum amount of power you can get maximum phase change and the ejection of the liquid. So in that case, ejection of the gases, basically liquid forms gas and that will eject, but embedded heater you may require more power. But here one disadvantage is that this titanium film which is used as a heater has to be insulated. On top of that, you have to have certain passivating layer, okay. So that it should not be directly contact with the propellant. So then propellant may react with the titanium and it may damage the resistance value, or it may change the resistance value, and maybe in due course of time it can be completely etched away if the propellant is highly toxic and reactive. So this is the alternate microprocessor structure which has been proposed by some group, and the basic feature of that alternate microprocessor structure is the following. The structure consists of two silicon wafer. Nozzle and holes for wire bonding are fabricated on the top wafer by bulk silicon etching. So that means here you have to have a separate hole for bonding the heater, which is inside the chamber. The vaporizing chamber and the micro channel with a depth of 2 micron is etched into on the front side of the bottom wafer. The heating resistance formed by titanium with 2000 angstrom thickness. The vaporizing chamber is connected with a propellant tank through a micro channel and inlet. Okay. Now the another class of the microthruster is sometimes known as the digital propulsion microthruster chip. Earlier are called analog. Here we call digital. Why? It is some kind of discrete propulsion in different direction you can give it. That is why it is known as digital. Here the basic principle is like that. Basic principle is same. Same means some propellant will be there, it will be vaporized and it has to be ejected, and then accordingly the third law of Newton's third law, some thrust will be created in opposite direction. But here what is being done, there are 3 dies are used. One is a top die where the diaphragms are made silicon membrane, basically diaphragm by thinning down you make some membrane. In the bottom is the middle die where you can etch some grooves, and each groove contain some propellant. Propellants are filled in each groove. In the bottom die is having some resistor which is polysilicon resistance, which we call the igniters, with the direct interconnects to bond pads. No electronics is here in the chip. So you can see here the four chambers, these are propellant chamber. Below the 4 propellant chamber there are say small spots you can see here in the bottom die, 1, 2, 3, 4. These are basically the heating elements. So they are connected and here bond pads are taken out. Now when you bond all the 3 pieces, substrate bonding you can do, all the 3 substrates are bonded together. Now by selectively or judiciously you can choose to heat any of the resistor below desired the chamber. So, lot of bonding inputs are there. You can select the inputs depending on your application. So, the selected, if you select the inputs by some algorithm programming, so selectively you can heat any of the propellant chamber, and if you heat the propellant chamber, so just above that propellant chamber which is the diaphragm, so that will be burst and the liquid will eject through that diaphragm. So accordingly, through which diaphragm liquid is ejecting, the thrust will tilt or orient or move the complete satellite. So if similar kind of thing, if you fix on the satellite top surface, bottom surface, side surface also, so you can have movement of the satellite either a tilted or directly pushing or little bit up or little bit down, accordingly you do it. By external selective circuit you can make it outside this complete device. That is why it is known as the digital propulsion micro thruster chip. Here that options is there, selective ignition and selective the ejection of the propellant through a particular diaphragm, and diaphragm is punctured, because if you hit the particular groove or particular the propellant chamber, so pressure will be created, and due to the pressure the diaphragm will be punctured and the propellant will be ejected. So that is the basic principle of the digital proportional microthruster chip. Now we propose a microthruster structure which is very simple and homogeneous also, and there you can see is a inlet is here. This is the heating resistor and this is the nozzle and the doplu, and what will be the size, optimum size, that we have to choose, we have to select, and what should be chamber size, that is also selected. So a structure like this can be made very easily in the laboratory. So here top wafer we use a diffuse, we just fabricate diffused resistors of 50 ohms, vaporizing chamber is 3 millimeter by 3 millimeter, nozzle is 30 micron by 30 micron, micro channels will be there, bottom wafer is a vaporizing chamber 3 millimeter by 3 millimeter, depth will be 150 to 200 micrometer. Now we just explain here one structure which we have fabricated in our laboratory at IIT Kharagpur. So this structure we have selected because we have got enough facility to create similar structure using the bulk micromachining technology. Here again we are using two wafers, one is the top wafer, one is the bottom wafer. In the top wafer you can see there is a propellant inlet, this is the tank, and through the tank here is a slow channel, and through channel the propellant will flow. This is the vaporizing chamber and this is the exit nozzle, and this is the complete width, and we have the heater in the bottom piece. The propellant inlet dimension in the top is 1 millimeter by 1 millimeter, bottom side 0.2 to 0.2 millimeter, because you see the propellant inlet here, the top dimension and bottom dimension are different. Top is 1 millimeter by 1 millimeter, bottom is 0.2 by 0.2. Micro channels of 0.7 into 0.25 into 0.05. Exit nozzles are this size 30 by 30, 50 by 50, 70 by 70. We have tested with different exit nozzle to see which is more efficient. Vaporizing chamber is here, this is the vaporizing chamber, it dimensions 1.5 millimeter by 1.5 millimeter. Vaporizing chamber bottom wafer, in top wafer, in both case you have etched, so that these are top wafer, this chamber is created, and bottom this chamber is created. Now you invert it and you just seal it, so that the complete chamber you will get it. Heating resistor is diffused resistance, we have used 250 ohm or 350, 400 different structures we have made it. Chip size total is 12 millimeter by 8 millimeter by 0.6 millimeter, is the thickness 0.6. Weight of the total chip is a 0.15 gram, a very low weight. So that we have fabricated in our laboratory, and you can see the cross sectional view of the top and bottom wafers. This is a top wafer, top side. Top side is this is one chamber, this is a propellant inlet, this is the exit nozzle. If you look here, this is the top wafer. Top wafer, there are two, one is the propellant inlet, another is the exit nozzle, and that if you see the planar view, you can see here top wafer top side, this is the propellant inlet and this is the exit nozzle, and the same top wafer in the bottom side is looks like that. Apart from these two, inlet and exit nozzle, there is a vaporizing chamber. In the top wafer also etched vaporizing chamber. Vaporizing chamber, it consists of both the wafer, top and bottom. So the top looks like that. Now if you look on the bottom wafer, basically one is the embedded heater. This is a heater, heating resistance, which we made by diffused resistance, boron diffused resistance of 300 or 250 or 400, three different resistances we have used. And here is the one micro channel here, through that so that in that channel the liquid propellant can push. This is the heating resistors. So the bottom wafer. Now total energy required to vaporize the liquid is equal to QT, which is the sum of the two parameters, which is Q1 and Q2, where Q1 is energy required to raise the temperature of the fluid to the vaporizing point. The temperature or energy required to raise to the vaporizing point, that is the Q1, and which is basically m into C into delta T, where m is the mass of the fluid, C is the heat capacity, delta T is the temperature difference from initial and the vaporizing point. And Q2, the second term is Q2, that is the energy required to vaporize the liquid at the vaporization form, that is the latent heat, nothing else. So m into LV, LV is the latent heat of vaporization, m is the mass. First, the room temperature to the vaporization point, that is a Q1, vaporization temperature, and from vaporization temperature to make it vapor, you have to have the latent heat amount of energy, so that is Q2. So total Qt is equal to Q1 plus Q2. Now thrust force corresponds to the reaction of the structure due to the ejection of hot gas at high velocity, that we have to calculate, and that is given by F equal to m star multiplied by V plus P2 minus P1 into A, where m star is the mass flow rate, V is the exhaust gas velocity, and P1 external or atmospheric pressure, P2 is a nozzle exit pressure, and A is a cross sectional area at nozzle exit. Typical thrust obtained out of this is 0.1 to 2 millinewton from this micro thruster. Now this is the fabricated device. Earlier was diagram, and this is the actual photograph of the device. Is a top wafer top side, bottom wafer top wafer bottom side. This is the embedded heater, you can see here in this structure. This is connected to that, the two bonding pads are there, and the crude way we have assembled to test. You can see one tube is going there. This is a inlet of the propellant, and some exit nozzles are here. If you apply power in a PCB, we have made it is a very crude device. Then the water propellant we have used, and that vaporized, and the vapor will come out of the nozzle with a higher speed, and we have tested the thrust by some alternate arrangement on the vapor from which the through exit path through which vapor is coming. If you put a very thin membrane, and on the membrane you put a laser beam, laser light, so if the membrane through the vapor, if it vibrates, so laser will be deflected. So from how much it is deflected, from there you can calculate how much thrust it is created. In an indirect way, you can just calculate the amount of thrust created by the device when the propellant is coming out of the exit nozzle. So that is in few in earlier slide it is shown is the 0.1 to 2 millinewton. So now thrust efficiency is one of the important issue. It accounts all the energy losses that do not result in kinetic energy, including what is that, because what are the energy you are supplying, it must be transmitted to kinetic energy. So that is, if something is lost, so then your efficiency will be lost. So, what are the parameters which can degrade the efficiency? Waste of electrical power, unaffected or improperly activated the propellant, that is propellant utilization, proper utilization propellant is necessary, loss of thrust resulting from dispersion of the exhaust, heat loss. So, all these issues you have to take care to get greater thruster efficiency. Okay. Now, the application of the micronewton, millinewton and newton thrust in different cases. So, east-west station keeping, attitude control, you need micronewton kind of thrust, and status is operational, is used nowadays. 15 to 20 years it's working, it's live. Millinewton kind of thrust required for north-south station keeping, that required for orbit changes, that is also operational. 0.2 to 10 Newton is orbit raising, it is active for 1 to 3 years, it is development, it is not yet done, it is under development stage. So, micronewton, millinewton and 10 Newton is required for orbit raising. These are the different applications. Now, overcoming translation and rotational perturbations in satellite orbits such as NSSK. What is NSSK? NSSK is here north-south station keeping, that is NSSK, and EWSK is east-west station keeping. So, now the overcoming translation and rotational perturbations in satellite orbits such as NSSK of satellite in geosynchronized orbits, or aligning telescope or antennas in low LEO or medium earth orbits. LEO is a low earth orbits and MEO is a medium earth orbits. For a typical NSSK task in a 35 kilometer orbit, a velocity increment of about 50 meter per second every year or 500 meter per second for 10 years might be needed. So, that means it is not instant use, in different time you need it. Potential missions such as interplanetary travel are also candidates for electrical propulsion. For example, return to the moon, mission to the Mars require high thrust and power. So, lot of R&D is going on in this direction, so that these things in miniature form can be produced, so that lot of innovative research can be carried out in the near future using the MEMS devices. So, here in this lecture I gave you a small preamble of a particular microthruster which is being used in micromachining technology, and it is also one of the program in our country's space program. So, let me stop here today. Thank you very much.